Hi, in this video, we're going to take a look at market basket analysis. Market basket analysis is where we try to discover items that appear together when they're being selected. So, by the name implies that we're looking at what items tend to appear together in a market basket, like in someone's grocery cart. So, why do we want to do this? Well, our goal is to identify patterns of, surprising patterns of items that come together. So, for example, we see that shampoo and conditioner tend to be sold together. Well, what we could do, we could promote a conditioner to improve the shampoo revenue at a store like Publix. According to legend, a very common co-occurrence is beer and diapers. So, if you were to discover that, and you would know if I wanted to improve like beer sales, I might put a coupon with the diapers. Maybe, I don't know. It'd be entertaining to do something like that. All right, so there's a couple of metrics that we need to talk about before we get into this. So we've got support, confidence, and lift. Those are the big three for market basket analysis: support, confidence, and lift. All right, so support is an indication of how frequently the item set appears inside the baskets. All right, so when I say an item set, we could be talking about like shampoo and conditioner, or we could be talking about like hamburger buns, relish. So when we talk about a collection of items, it could be any number of potential items. Of course, it's going to of course be 2 or greater because of the nature of the analysis. So support is equal to the frequency that we observe the items coming together, and then the number of baskets that we take a look at, and let me put that there. And so support of A implies B is a frequency of A and B appearing together divided by N. So the difference between these two, here support for one item is just the frequency of that one item appearing in a basket divided by the number of baskets. The support of A leading to B is a frequency of A and B appearing together in a basket divided by the number of baskets. Okay, so one thing you'll notice is that I've got an arrow here, but here the frequency, there really is not a direction. So the support of A, arrow B, and the support of B, arrow A, it's going to be the same. Now, confidence. Confidence is an indication of how often the rules have been found to be true. All right, so the confidence of A, arrow B is equal to the probability of A and B divided by the probability of A. So you'll know that from conditional probability, this is the probability of B given A. So this arrow notation is, we're interested in B given A. We know that A has occurred. What's the probability of B? So in this situation, we see that someone is using an app to scan the items that they have in their basket before they put it in their basket. And the app detects that they have hamburger buns. Okay, so it's highly likely that they're going to be needing ketchup. Now, as a store, I want them to buy ketchup today. I don't want them to use the ketchup in the refrigerator. I want them to buy ketchup now. So what we could do on their phone, we could send them a coupon and go, hey, we have a discount on the ketchup that you love. So that way they're more prone to buying a full bottle of ketchup instead of using the bottle of ketchup that's sitting in the refrigerator. And thus we make more money. And this will be the frequency of A and B divided by the frequency of A. Is how we compute the empirical probability. All right, now lift it gives us a measurement of how much of an improvement we have from using the model compared to not using the model. So here is going to be the correlation between A and B in the rule A given B, or B given A. The correlation shows how one item set A affects the one item set of B. All right, so lift A leading to B is equal to the support of A and B divided by the support of A times the support of B. All right, so remember lift. Lift starts at 1. The bigger the lift is, the better. And so here, if we get a lift of 2, that's usually a pretty big deal. But we have to double check anytime I'm dealing with lift, or I always need to double check to make sure that I have a significant number of baskets involved. So something about this, a lot of times when we have a few observation frequencies, it can look like we have a high lift when really we don't. Or it's not really that significant. So we always need to consider the count whenever we do market basket analysis. I find that the best way to proceed with this is to look at the high count item sets first, and then find the ones that have better support, confidence, and lift. All right, the density indicates how frequently items appear together in a basket. It measures how sparse the transaction item matrix is. If density is high, it is more common for more items to appear in a basket. If density is low, few items are purchased together. Let me change that. All right, so in R, the most common package for market basket analysis is the A rules package. And the a priori function is by far the heavy workhorse of this package. So the major parameters of this is that it's going to be the data, which will be usually a DataFrame or binary matrix that can be conversed into a transaction object. We have parameter, we have appearance, and we have control are also things that we can plug into the function, and we'll talk about these when we get to the function itself. So if we're only interested in the rules themselves and not the rest of the details, we can use the appearance parameter in the a priori function to specify if we want the item on the left-hand side, the right-hand side, or both. So in that situation, maybe I'm only interested in what, like I'm pretty good at, or we're having a good time selling hamburger buns. And so that's my left-hand side. Once I see that there's hamburger buns, what should I prompt them to? Or maybe I want to see what's leading to hamburger buns. Then I'm interested in the right-hand side. All right, so let's take a look at the code. So we're going to go ahead and use the A rules package. We're going to use a groceries data set. And this is a class of transactions. So the original, this can be represented either as a transaction item, or we can have a binary matrix indicating, so each basket is a row and each item is a column. And 1 indicates that that basket contained that item. A 0 means that item was not in the basket. And now if I want to look at individual rules, what we use the inspect function. So I can see that in the first basket, we had citrus fruit, semi-finished bread, margarine, and ready soup. In the second basket, we had tropical fruit, yogurt, and coffee. And this is actual grocery store data, by the way. All right, so let's take a look at the summary of the groceries data set. All right, we can see that we have just under 10,000 rows. We have 169 columns and a density of 0.03. The most frequent items are whole milk, other vegetables, rolls and buns, soda, yogurt, and other. All right, so here what this is telling me, it's telling me the frequency of items in the transactions. So we can see that it looks pretty smooth, that it's just decreasing as we increase the number. So I can see that it goes 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. All right, skips 16, is that right? Nope, 16 is here. 17, 18, 19, 20, 21, 23, 24, 26, 27. All right, so skip 25. And you'll notice that out here it starts skipping numbers. And and it's pretty common for it to be this kind of this decline setup. And we can see that the median number of items is 3. The maximum is 32, and the minimum is 1. Not surprising. And so here, we talk about frankfurters, sausage, meats, and sausage. Sausage, sausage, meat, and sausage, and liver, loaf, sausage, meat, and sausage. We'll look at the code that brought that up real quick. Oh, that just came out from the, it's just part of the summary function. All right, now let's take there's the item frequency plot that generates a bar plot. And so here I'm telling it to only grab the top 10 from the groceries data set. All right, so the most frequent item is whole milk, then other vegetables, rolls and buns, soda, yogurt, bottled water, root vegetables, truckable fruit, shopping bags, and then sausage. And this gives you relative frequency. All right, so now let's actually do let's start building some rules for our market basket analysis. All right, so what I want to do in the a priori function, I'm going to first specify my data, and then inside for the parameter, I'm going to create a list. All right, now what do I want out from the a priori function? I want to have rules coming out. I'm going to say that I want a maximum length of 2. All right, so what this is saying, it could be like if hot dog buns, then hot dogs. Another type of rule could be if hot dog buns, then hot dogs, then ketchup. That would be a length 3 rule. And so that would be like a chained rule like that. And that would be different from if hot dog bun, or if hot dog buns, then hot dogs. That would be different from if hot dogs, then ketchup. The 3 as a chain is different than the 2 separate. Now, confidence, what I'm saying here is what is the minimum confidence to be included in my rule set? What's the minimum support? And what is the minimum length? And usually you want to just put 2. Now, for appearance, what we do, we say, hey, I'm only interested in certain items, and I can specify either I want to look at rules with these on the left-hand side, I can look at rules with these on the right-hand side, or I could look at them on either side of the conditional probability. And here we're saying either side on these more frequent ones. All right, so when I do that, it reminds me what the parameters were. Gives us a lot of information. The minimum support count is 491. All right, so this only ends up giving us 6 rules. Now, that's not very many. The reason for that is that this is rather high for the support. Honestly, if I was doing this in real life, I'd probably put 0.01, but that would be a lot, or that would give a lot for the purpose of a lecture. And for the printout originally when I had 0.01 just had too many rules. So I went ahead and just increased the minimum support, and that decreased the number of rules to something that I can print out relatively easily for you guys. And all of the rules were length 2 because we set that as the minimum and the maximum. And we can see, the range of support values, the summary statistics for confidence, lift, and count. So minimum lift of 1.2. Remember, 1 is interpreted for lift. 1 means that we're not doing any better using the model than if we didn't have the model at all, if we just did the naive thing. One thing that I feel is the most important item to start to work with is to really look at your higher count like rules first, and then look at the rest. I would start out by cutting on doing a minimum value for count, everything above that keep, and then start looking at support, confidence, and lift. Because otherwise, if your count is low, then it could just be random chance. and you can't be confident that the other statistics have converged. And so you can't trust it. Don't go with it. All right, so here we're going to look at the most the highest count rules that we get. I'm using the inspect function to get it, and I'm sorting so that I have the high count up top. So other variables, the whole milk, and whole milk to other variables. We can see that because they appear together in a basket, there isn't a conditional probability point of view, but I do have a different confidence. So I can see that other vegetables leading to whole milk has a greater confidence in whole milk leading to other vegetables. So what we could do is when we see, like, someone scans with their phone some other vegetables to put in their market basket, then we can go, hey, did you know that there is a sale on whole milk? And we want them to go to the dairy section and pick up a thing of milk, even though they don't need it. They have enough milk in a refrigerator. Yeah, and so usually you're going to have this phenomenon where we have symmetric rules having the same counts, but one will have better statistics than the other, specifically confidence. But like this rule here, with a lift of 1, I'm not confident that I'm going to get much of an improvement. Now that is rounded, so it might have been like 1.4. Because I'm using R Markdown to print everything, it doesn't really display a lot of digits well, so I limit it to 1 digit to kind of shrink everything down. So it might be a better rule to use. I'd have to double check, but these other 4 rules are more promising in my opinion because they have better lift. All right, so now let's go ahead and let's change some parameters and do this again. So here, once again, I'm trying to get rules out of the a priori function, but now I'm going to go with a max length of 3. So I'm chaining 3 items together. I'm going to have 2 arrows. I'm saying a minimum confidence of 0.1, a minimum support of 0.02, and minimum length of 2. So I can see that we almost get 200 for the support count. All right, this part of the code just gave me a ton of output, and so I went ahead and just suppressed the code. At home, go ahead and uncomment this out so that you can see what's going on. I didn't want the document to get crazy long. All right, now, one thing that's going to happen is that if I have hot dog buns implying hot dogs, and I have hot dogs implying ketchup, and I have hot dogs implying hot dog buns implying ketchup as rules, there's a redundancy in there. So what we want to do, we want to go through and we want to remove our redundant rules. And fortunately, the A rules package has a way to detect, is this a redundant rule? And if it's redundant, get rid of it. So in this case, it's 0. Before I played with the parameters, there were redundant rules, and I just went through and removed them. And also, something that we can do to make it easier to analyze the output, to analyze what we get, there is a all caps data frame function that converts our rules to a data frame. And so whenever I have my data frame, I can go through and find like rules that I find interesting. So here, I want to look at the data frame where the right-hand side was equal to whole milk. And then I want to look for the pattern of sausage or other vegetable or yogurt or soda. And here I get my rules. All right, so let's see, what do I feel? So I think that these 2, I would say, are the best to look at. So yogurt leads to whole milk. Other vegetable leads to whole milk, which we've already seen. And then this is in 1.2. Might want to go with it depending on the our resources. Sausage leads to whole milk. And remember, when I pulled this up, I said I only wanted to look at rules with the right-hand side being whole milk. Now, when I take a look at, sorry, I got ahead of myself. This part of the code says to get rid of redundant rules. The isRedundant function gives a logical vector. Now the A rules visualizes the output from the A rules package. Go figure. I know you're surprised. All right, so one thing I can do is I can just go ahead and plot the a priori output. And it plots all 120 rules for us. And by default, the x-axis is support, confidence is the y-axis, and lift is the color. So I'm looking here, and I like whatever rule that is, that one is catching my eye. I'm interested in that because that's got pretty good on all three. Now we also have the option of switching what's going on. So here we're putting confidence and lift on the axes, and support is the shading. And so if I want, I can plot these three metrics in all 6 ways. We also do a scatter plot and see what happens. So it gives, so if I say scatter plot, it does support, confidence, and then lift as shading. We can do a 2-key plot. All right, so what this does, this enables me to see what's the difference between the order 2 rules and the order 3 rules. Order 3 rules, we can see that they've all got low support, but they have high confidence. All right, and then order 2, it's kind of spread out. Like these rules over here are the ones that are interesting me right now. All right, we can also use the matrix method to print out or to plot some rules. Now, when you do this, it gives some output by default. So we can see like what's the antecedent, the left-hand side, what's the consequent, the right-hand side. And these numbers correspond to the numbers up here in the output. And so this way we can kind of try and find where do we have better lift. We also do a 3-dimensional matrix. So here we have confidence lift on the X and Y axis, and then we have, we have confidence support on the X and Y axis, and then we have lift as the Z axis. So we have antecedent, consequent, and then lift vertical. A lift of 3 looks really interesting, but I'll bet you money that that's going to be a low count rule. So I probably wouldn't end up using that. But if I see a lift of 3 and it appears frequently, I probably want to dig into that. All right, now the HTML widgets engine gives us the ability to generate like a network, like a graph, in terms of like a graph theory graph, and with like nodes and edges. I couldn't get that to run in R Markdown, so I suppressed it. But on your machine, you can go ahead and take a look. It ran for me just fine when I was not using R Markdown. And now we can use a parallel coordinate system to plot. So parallel coordinates is when I make a vertical line for into an axis, basically. So I've got 3 different axes, and we can, if I was to dig in, I can see how these are moving along. And this displays like a matrix of dots to show you the values that are happening between the left-hand side and right-hand side. Here in R Markdown, it doesn't visualize very well because it's getting stuck into a Word document. But if you put it on your machine, it'll look a lot better. All right, that's all I've got for now. I hope you're staying healthy. Take care and goodbye.